So, today we are going to solve, this is going to be a tutorial class, and we would be looking at a specific problem and would try to use the shell mass balance, more correctly the shell species balance, to evaluate certain quantities. And as an example, we have taken the dissolution of a drug inside our intestine. So, as you are aware of, many of these drugs are time release drugs. That means, it is going to dissolve slowly in the juices present in our intestine, and it is going to be active over a prolonged period of time. So, this kind of time release drug, the way they are manufactured is that the drug is going to be coated with a specific coating through which the drug molecules will slowly diffuse and get dissolved in the intestinal juices. So, for as long as we have this diffusion, so it is not going to be a rapid diffusion, it is not going to dissolve instantaneously, it is going to dissolve and be active over a prolonged period of time. So, we are going to start with a specific drug which is probably made in a pellet of cylindrical sizes of certain radius and length, and it is going to be coated with an inert coating. So, it does not serve any purpose other than it reduces the dissolution of the drug. So, the drug has to diffuse through this coating, reach the other end where the convective conditions will result in a specific convective mass transfer coefficient. So, the drug molecule that diffuses through the inert layer comes on the outside of the inert layer and will be carried away from the cylindrical shaped drug and will be absorbed at our intestine. So, this is the problem which we are going to model and we are going to solve for it. So, the specific problem that we are going to look at is, as I mentioned before, a timed release drug is slowly dissolving in the intestine of a person, and we are going to use the steady state approximation, and we will assume that the drug is a rod of overall radius r naught and it has a length equal to L, and the time released action, as I have mentioned before, is accomplished by putting an inert coating on the drug through which the drug diffuses with a diffusivity which has been denoted by DAB. At the inner edge of the coating, let us look at the figure which I have drawn for this. At the inner edge of the coating, so this is the drug, the white portion that you see here is the drug, it is cylindrical in shape with two end caps, and at this point, that is at the inside of the inner coating, at the inside of the coating, that means that R equals R I, where R I is the radius of the cylindrical drug pellet. The concentration of the drug is maintained, the mole fraction is maintained at X A equals X A I, and the digestive juices which are present on the outside of the drug that we have, it maintains a coefficient of mass transfer which is similar to that of convective heat transfer coefficient as denoted by KAC. So, any drug molecule which comes on the outside through diffusion through this inert layer, which is the blue shaded region, the drug molecule will then be moved away by a convective mass transfer coefficient, and the concentration at the outside of the drug at a point far from it is maintained at 0 concentration. So, X A infinity is equal to 0. The drug, it has also been assumed that the drug is not going to be released by these two end caps. So, drug is only going to be released through the inert core, that is through the cylindrical surface of the drug. So, as I said, on the outer surface, the digestive juices provide for a mass transfer coefficient which is denoted by KAC, units of meter per second, and the amount of drug within the intestine can be approximated as x a infinity to be equal to 0. So, at a point far from the drug, the concentration is assumed to be 0, and the drug is also not released by these two end caps. And you can also assume that the total concentration of all the species within the coating is Ct, which is a constant. So, there can be other species present in this coating apart from that of the drug, and the total concentration of everything which is present inside the coating material is denoted by C suffix t, which we can assume to be a constant. And we will also assume that it is a diffusion only process, and we need to calculate the rate of drug release in milligram per hour in the intestine. So, how much of drug is going to diffuse through the inert layer, come to the other side and get convected out of the drug into our intestinal juices. So, this is we have to need to calculate the rate of drug release in milligram per hour, and the geometric and other information which are provided is the inner radius of the drug, that is without the coating is R I, which is 3 millimeter, and when you put the inert coating on it, the radius is going to be equal to R 0, which is 5 millimeter. The diffusion coefficient is 10 to the power minus 10 meter square per second. The convective mass transfer coefficient is provided as 0.1 meter per second. The entire length of the drug is 5 millimeter. The concentration, including the drug, concentration of all the species present in the inert material, inert cover, including that of the drug, is 0.4 kg per meter cube, and XAI, which is the mole fraction of the drug at the inner layer of the coating. That means, at this point is equal to the mole fraction is equal to 0.9. So, what we need to find out is the rate of drug release in milligram per hour in the intestine. So, you can see that this is just a diffusion only process, and if we take a thin slice in the inert cover of the drug, then we should be able to write what is the shell species balance. The species in this case is that of the drug. So, the drug diffuses through the inert core, reaches the outside, and will move out of the drug into the intestine. So, it is a diffusion only, one dimensional diffusion only process, where the drug is moving only in the R direction. So, so therefore, we understand that the concentration or the mole fraction of the drug is going to be a function of R. It is not going to be a function of length, that is Z in here, and definitely it is not going to be a function of theta. So, irrespective of the position of the shell with respect to theta, the concentration, the mole fraction is going to be same at all theta. So, we are going to assume a shell which lies inside the inner core, and we are going to make a balance, and no reaction is taking place. So, we are going to make a balance of the drug molecules coming at the core, coming at the shell, going out on the other side on the other side of the shell, and in the shell there is no reaction which is taking place. So, the flux multiplied by the area, and the area is simply going to be equal to twice pi r times L, that is the inner surface area of the imaginary shell. So, twice pi r times L, that is going to be the area through which the diffusion takes place. So, that multiplied with the radial molar flux of the drug, that is going to be the amount of drug, moles of drug, which is coming to the inert surface per unit time. On the other side, the radius is going to be of the imaginary shell, the radius is going to be r plus delta r, and we will have another flux which goes out of it. There is no generation term, no depletion term, that is no reaction is taking place, and at steady state, rate of drug molecules in, rate of in minus rate of out plus 0, since there is no generation, and since it is at steady state, the right hand side of the species conservation equation will also be 0. So, essentially what we are saying is that the rate in minus rate out is going to be equal to 0. So, that is the species balance equation, the species in this case being that of the drug. So, we will start from that point. Therefore, our is I hope the figure is self explanatory. So, the drug, the coating, the outside where we have the digestive juices, the convective coefficient, and the boundary conditions provided are at the inner core, the mole fraction is provided, and at a point far from the drug, the concentration of the drug in the digestive juices would be equal to 0. R R 0, the values are provided, the length is provided, the total concentration of all the species present in the inert core is provided, and the mole fraction of the drug at the inner core is also given. So, we will start with the derivation of the governing equation. So, my governing equation in this case, as I have mentioned, in which is twice pi r times L. So, that is the area multiplied by the flux evaluated at any r would be equal to twice pi r plus delta r times L, that is the outside area of the imaginary shell multiplied by n a r, everything evaluated at r plus delta r. Since there is no reaction and since we are talking about 0 as steady state, this is going to be equal to 0. So, what you get by dividing both sides by r, what you get, and taking using the definition of the first derivative, you would simply get this to be equal to 0. So, this is your governing equation, and which can then be integrated in order to obtain r times, and after you, since it is a diffusion only process, you can simply write N A R to be equals to minus D A B times C, which is the total concentration, times d x a by d r. So, you plug this in here, and what you would get out of this, and since C is a constant, DAB is a constant, we can cancel this, and what we have then r times dx dr and d dr of that at steady state would be equal to 0. So, we have used Fick's law for a diffusion only case, plugged that in for the molar flux of the component A in the r direction and the governing equation, and since C and DAB are constant, this is going to be my governing equation. So, once you integrate it twice, you are simply going to get x a to be equal C1, where C1 is one constant of integration times ln r plus C2. So, this would be the profile of x a in the inert material. Had this been a case of constant surface area, for example, in a plane wall, the distribution is going to be linear, but in this case, as the drug molecules move upward, it experiences larger surface area. So, for these type of cases, for cylindrical cases, the concentration distribution, exactly like temperature distribution, is going to be a logarithmic function of the radial position. So, therefore, the mole fraction of A, which is the drug, inside the inert material in absence of any reaction will simply follow a logarithmic distribution, and that is what we have obtained in here. And we now need to solve for C1 and C2, the two constants of integration, using the boundary conditions which are available to us. One boundary condition is straightforward, that is known concentration at a specific location. We understand that at the inner core of the inert material, the mole fraction of A, the drug molecule, is specified. So, the first boundary condition, the boundary condition 1, would simply be equals that at x A, the mole fraction is going to be equal to xAi at R equals Ri. So, this is going to be the first boundary condition. So, when you put the first boundary condition in here, it is simply going to be xAi is equal to C1 times ln Ri plus C2. So, this is going to be my relation 1, and the second boundary condition, the boundary condition 2, will be on the outer surface, on this surface, on the outer surface of the coating. So, at the outer surface of the coating, the diffusive flux of the drug molecules which are reaching. So, if I take this as my as an enlarged view of this region, what we would get is the diffusive flux which is reaching at this point must be equal to the convective flux. So, diffusive flux must be equal to the convective flux. So, the amount of A which reaches by diffusion to the outer layer of the coating must be convected out due to the convective condition maintained by the digestive juices with a convective mass transfer coefficient denoted by Kac. So, if we write the equivalent of Newton's law to denote the convection of species and the Fick's law for the diffusion by which the drugs reach at this point, the convective diffusive boundary condition together would give us minus dAb times total concentration dXA dr evaluated at R equals R naught is equal to Kac, that is the convective coefficient, times concentration at R0 minus concentration at infinite distance. Concentration at infinite distance. So, this is essentially the diffusion and this is convection. So, on the control surface which characterizes the outer surface of the coating, diffusion of A must be equal to the convection of A away from the drug into the intestinal juices. So, what we can write this as minus dAb and dXA dr. If you look at dXA dr from here, you are simply going to get this to be equal to dXA dr is going to be C1 divided by, it is evaluated at R naught. So, this is going to be C1 by R naught. If you integrate it, if you differentiate it once, dXA dr would be C1 by R, and since I am evaluating it at R equals R0, it is simply going to be C1 by R naught. So, this is going to be the left hand side, and on the right hand side it is going to be Kac times XA0. We understand that CR0 is XACR0 is equal to XA0 times Ct. So, C and C XA infinity is 0. So, this part is going to be equal to 0, and what I have left with after I cancel Ct from both sides, what I am left with Kac times XA0. So, this is one condition which is obtained by equating diffusion and convection and identifying that C naught which is C infinity which is XA infinity multiplied by Ct, and we know that C infinity is XA infinity is 0. So, therefore, this part is going to be 0. No drug, you have very small concentration of drug in the intestinal juices. So, this can be equated to 0 and we cancel Ct from both sides. So, therefore, you can get the expression of C1 as equals minus Kac times R naught divided by dAb times XA naught. So, the expression for the first integration constant can be obtained by through the use of the second boundary condition. So, this is what we have obtained as the expression for the first integration constant. this can now be put in here. So, therefore, you would get C 2, which is the other boundary condition, would simply be equals x a I minus C 1 ln r I, just this one, and then I am going to put the expression for C 1 in here to obtain what is the expression for C 2 going to be. So, I write C 2 once again in here as x a I minus C 1 ln r I, and I have already obtained C 1 to be equals minus k a c r naught by d a b times x a 0. So, I think it is straightforward, but if you have any question, please email to me, and if there are any questions, I will try to clarify that. I will try to clarify that. So, with this I come to the expression of C 2, and once I put this in here, what I am going to get is C 2 is equal to x a I plus, because of this minus, it is going to be k a c r naught by d a b times x a 0 ln r I. So, now I have an expression for C 2 as well. So, if I go back to my original expression of x a to be equal to x a to be equals C 1 ln r plus C 2, and plug in the values of C 1 and C 2 in here and do a little bit of simplification, what you are going to get is x a is equal to k a c r naught by d a b times x a 0, which is the expression for C 1, times ln r I by r plus x a I. So, this is the expression, total overall expression for x a that you are going to get out of this relation. So, this is the final expression x a to be equals x written in the same way, in a more general way, times r naught by d a b times x a naught ln r I by r. So, what I need to do next is we need to plug in the values in here, and the values that are provided in the problem, x a I as 0.1 meter per second, d a b is provided as 10 to the power minus 10 meter square per second, r naught is 5 into 10 to the power minus 3 meters, x a I is equals 0.9. So, when you put this one k a c r naught by d a b, when you plug in the numbers, they will be equal to 5 into 10 to the power 6, which would give you x a to be equals x a I plus 5 into 10 to the power 6 x a naught from this relation ln r I by r. So, now I have the first part of the problem, which asks what is the first part of the problem, that we need to calculate the rate of drug release. So, the first thing that I should do is find out what is the concentration distribution. So, I have got an expression for concentration distribution in here. I will start this, I will write it once again, that x a is equal to x a I plus 5 into 10 to the power 6 x a naught ln r I by r. Okay. So, we realize that at r equals r naught, that means at the outer edge of the inert coating, my x a would simply be equal to x a 0. Let us call it at x a 0. And we understand that at x a I is equal to 0.9, the value of Ri is equal to 3 into 10 to the power minus 3 meters, and R naught is equal to 5 into 10 to the power minus 3 meters. So, when you put these values in here, so what you are going to get is x A naught, which is the concentration, the mole fraction of component A at the outside of the inert layer, is simply going to be equal to x A I plus 5 into 10 to the power minus 6 x A naught, and ln instead of Ri it is going to be 3, and R naught it is simply going to be equal to 5. So, x A naught would be equal to 0.9 divided by 1 minus 5 into 10 to the power minus 6. When I bring this x A naught to this side, 5 into 10 to the power minus 6 ln 3 by 5, and this would turn out to be 3.527 into 10 to the power minus 7. So, it essentially tells the concentration of the drug on the outside is simply going to be 3.5 into 10 to the power minus 7. The next that is remaining is rate of drug release, which has been asked, rate of drug release into the intestine, that as a drug designer you must find out, and we understand that since I know x A naught, I should be able to equate the multiply the convective movement of the drug away from the inert core, away from the outside of the inner core to the digestive juices. So, I am going to have this as K A C multiplied by x A naught minus x A infinity times whatever be the total concentration in here. So, ideally if you look at the concentration, the convection, total amount of convection of this species away from the outer core of the inert material is simply going to be the convective mass transfer coefficient multiplied by the concentration difference. So, that when you multiply with the area, outer area of the inert coating would give you in kg per second, in SI units in kg per second, what is the total amount of drug that will diffuse through the inert layer, reach the outside of the inert layer, and by a convection process initiated by the movement of the intestinal juices inside the intestine, that is going to get dissolved. So, it is going to give you the dissolution rate of the drug in our intestine. So, if you see, this is the area, this is the convective transfer coefficient, and this is the concentration difference. So, this is area, this is convective mass transfer coefficient, and this is nothing but the concentration difference in here. We understand that this x A infinity is assumed to be 0, that means no drug exists in the intestinal juices. So, if I substitute, if I put the expression for area, it is simply going to be twice by R 0 times L. It is a cylindrical area, and only the side area is going to contribute. The end caps are not going to, the end caps they do not contribute to the movement of the drug. So, the area over here is simply going to be, the outer area is going to be twice by R 0 times L times K A C times C T times X A 0. So, this is the total amount of drug which gets dissolved in the intestine, and when you put the values in here, twice pi times R naught is 5 into 10 to the power minus 3 in meters, L is again 5 into 10 to the power minus 3 in meters. The value of K A C is provided as 0.1, this is in meter per second. Then C T is given, the total concentration of all the species present is given as C T as 0.4 kg per meter cube into the value of x A 0, which you have obtained from here. So, into 3.527 into 10 to the power minus 7. This being a mole fraction, obviously it does not have any units. So, if you look at the units over here, the total unit is simply going to be equal to in kg per second. So, the rate of drug release we have obtained in SI units, which is in kg per second. When you evaluate this, this is going to come to be equals 8 into 10 to the power minus 3 milligram per hour. So, that is the dissolution rate, of the drug in the intestine. So, you see that this is a pretty simple problem, which is where you start with a balance in an imaginary shell across which one component is diffusing. It is a diffusion only case, so you do not have to consider convection. So, the Fick's law, the simplified form of Fick's law only for diffusion is to be used in this case. So, you get d dz of NaZ to be equal to 0, and it is a d dz of R NaZ, d dr of R NaZ to be equal to 0. Since it is a cylindrical system in which as the drug molecules diffuse out, it encounters a bigger area, larger area. So, therefore, the distribution of the concentration or the mole fraction of the drug inside the inert material is going to be a logarithmic function of the radial position. There are two boundary conditions which are needed. We identified the boundary conditions to be a known concentration at a given location, which is at R equals R I, and at the outer edge of the inner layer we have equated, taking that to be my control surface, we have equated the diffusive flow of drug up to that point through the solid inner core must be equal to the convective flow out of the drug molecule from the outside of the inert core. So, equating the diffusion and the convection, we could evaluate what is the second boundary condition, and putting the second boundary condition into the expression of x A, which is the mole fraction of A, we could also obtain what is the first constant of integration. So, we have obtained this as the concentration profile. After plugging the numbers in, we have obtained what is the concentration distribution, and since we know at R equals R naught, x A is equal to x A naught, we obtained what is the numerical value of x A naught after putting in the values that we know, and the rate of drug release is simply the product of area, the convection coefficient, and the concentration distribution. See the concentration distribution here, which is the common practice in many mass transfer cases, is expressed not in terms of concentration difference, but in terms of the mole fraction difference, and the mole fraction multiplied by the total concentration would give you the mole fraction of component A at two locations. We know at infinity, at a point far from the drug, the mole fraction is 0. So, we put that equal to 0, and we get a compact expression and obtain what is the dissolution rate of the drug in our intestine. So, next I would also upload a few other problems on mass transfer that you can try on your own, and if there are questions, I would provide you with the answers as well with short pointers of how to solve them, and if you have any questions, then we can discuss it further offline. In the next class, what I am going to do is the same way I have developed the equation of energy and equation of conservation of momentum, the same way I would do it for a species balance equation, which would be straightforward, since we are only going to deal not with momentum transfer, heat transfer, we are simply going to write the conservation equation of a species. It could react with another species, it could be a process which is transient in nature. So, I am going to derive the general form of the concentration distribution of one species as a function of x, y, z, the positional coordinates as well as time. And when I have that in cylindrical coordinates, Cartesian coordinates, and in spherical coordinates, then you as before no longer would need to do the shell shell mass balance anymore. You simply pick the equation that in the right coordinate system and start with the species transport equation with the at the appropriate coordinate system. Let us say cylindrical coordinate systems. Cancel the terms using simple logic, and what you would get at the end of the process is your governing equation for the species transport in that case. It is going to be extremely important to deal with cases where the geometries are complicated, where you may have the concentration varying in x and y directions, or more importantly when we are dealing with transient mass transfer situations. So, that would be the topic of the next class.